Welcome back. We are in this lesson going to continue our study of geometric algebra. We're trying to get prepared to understand these relative frames and paravectors. We're exploring three-dimensional geometric algebra. We're taking a break from space-time algebra. And today we are going to talk about rotations. Now, in the last lecture, we did some preparation, which we're going to redundantly go through again today, hopefully a little quicker. I think last time I said, we're not going to talk about reflections, but upon reflection, I've decided that I don't think there's a better way of understanding rotations in geometric algebra than going through reflections. So that is going to be, in fact, our method today. And let's begin.
Okay, so let's begin with a little bit of a catch-up, right? I never object to going through things again in multiple lectures because these are just things that need to be automatic and they're worth repeating. And as long as we're learning, it's okay to go over the same ground again in different contexts. So here we go. We're dealing with, we're headed towards this understanding of rotation. So we're going to start building things up again. Reminder that two vectors, A and B, take their geometric product, A dot B, A wedge B. We know that A dot B is this inner product, which is the magnitude of A, magnitude of B, times the cosine of the angle between them. And A wedge B, we know, is going to have a magnitude of the area of the parallelogram between the vectors A and B, which is the magnitude of A times the magnitude of B times the sine of the angle between them, multiplied by some orthogonal bivector WV, which is an orthogonal bivector that is a unit orthogonal bivector, and meaning that we can write it as W hat V hat, and it is in the plane of A and B. So so this is a bivector just like this is. Then once we've done this, well, we can take this expression and just rewrite it this way, which is very critical. So the magnitudes come out in front, and you end up with this essentially magnitude 1 exponential form, right? Because we're obviously going to turn this into an exponential in the next line. And we do that right away. We take AB, we multiply it by the exponential of W hat V hat sine theta, and we can do this because we know that W and V multiply to -1. This is something we kind of showed in the last time. WV is minus WVVW. This becomes V squared, which is 1. Then what's left is W squared, which is 1. And you get -1 for that one flip you needed. So we're going to call that guy I, little I, to represent the bivector that defines the plane between A and B. So ultimately, I lost my magnitude of B here. And so ultimately, we know now that we can write the space-time product of A and B as the magnitude of A times the magnitude of B times e to the I theta, where theta is the angle between the two vectors, and I is a unit bivector that defines the same plane as A and B. Okay, so with this form available to us, we also need to, let's remind ourselves, we learned last time, the projection of a vector x onto another vector y. And this is good for, by the way, any dimensionality, right? There's nothing in here about 3 dimensions of space-time, right? The only thing that would make this 3-dimensional is if we defined A and B precisely to have 3 independent components, but we haven't even specified that. So this is definitely true so far for every dimensionality. For every dimensionality, the space-time product of 2 vectors can be written in this form. Then again, for every dimensionality, you can project one vector onto another. And we know that we learned last time that the parallel part of the projection is the magnitude of A times the cosine between the angles. Well, I said A here, so this probably should be an A, right? An A vector. Notice these are not unit vectors. So the magnitude of x times the cosine between the angles of the two vectors times a unit vector in the direction of a. And that, of course, is a aligned, x is the component of x aligned with a. Of course, that this is something we may have learned from regular trigonometry, but we know that that's also expressible in this form because the magnitude of a unit vector is 1, so we can write it this way as x dot a hat in the direction of a hat. And then if I replace a hat with its definition, which is a over the magnitude of a, which is a simple replacement to make, then obviously I can take this a hat out and I will get x dot a vector, right? Now a is a vector, so I put a vector symbol up there just to be absolutely clear. Although I guess for consistency's sake, I probably shouldn't have done that, right? Because I haven't done it before. Although I did it on x, right? So why don't I do it on a? Yeah, I should be doing it. I should be doing it. So I'm going to put in these little vector symbols, the full vector symbol. And that should probably be the full vector symbol here as well, right? It's the magnitude of a vector. And then a hat over the magnitude of a. And then this gets to a inverse how? Okay, this gets to a inverse because this guy here, see, this is why it's worth doing over again. You keep kind of having to remind yourself. This is equal to a over the magnitude of a. That's what a hat is. And then you get another factor of the magnitude of a down below, which is a over the magnitude of a squared, which is the definition of a inverse, right? So we end up with x dot a times a inverse, and that equals the projection of x onto a, right? So that's a nice thing to know. Yeah, see, getting from this statement to this statement is something you should be able to think about and do. It's just we're plugging in the definition of a hat. We get a hat over another factor of the magnitude of a, which is a over the magnitude of a squared, which multiplied by a is a squared over the magnitude of a squared, which is a inverse. Now, it's worth noticing that this is a place where the three-dimensional geometric algebra and the space-time algebra actually do have a meaningful difference, right? Because if we look at a vector, say b, right, in the space-time algebra, well, what if b is space-like, right? Which would mean that the magnitude of b is less than 0. This would be then if for example if b squared was less than 0, say that was the case, well then b over the magnitude of b squared, right? If you multiply that by b, you're going to get a number on the top that's less than 0 and a number in the bottom that's greater than 0. So this is going to equal minus 1, right? So it won't be the inverse. It'll be the opposite of the inverse. So this is where studying three-dimensional geometric algebra might actually cause a problem to expand to other geometric algebras. So the rule that works for four-dimensionals for the space-time algebra is that B inverse is B reverse over B reverse B. Now, a vector is its own inverse, but what ends up effectively happening is this becomes B over B squared, which actually becomes, and B squared is going to be less than 0. So when you multiply it by B, you get B squared over B squared, which will equal 1. So there's something to keep an eye out is in your whatever geometric algebra you're working in, you really have to understand how to calculate the inverse. So let's continue. The next thing we did is we calculated x's rejection onto y, right? So the rejection of x onto y, I think same problem here, this y I should replace with an a, right? And the rejection is simply the vector itself minus the projection, right? So this is one of those little sort of geometric algebra tricks that you do in these proofs. You can always multiply geometric product by AA inverse, right? Because that's just 1. So I can distribute the AA inverse to get x AA inverse, and then x dot A inverse AA inverse, because the projection part is x dot A inverse, where I am missing a little arrow there, right? This is supposed to be a little arrow right here. So now, once I've done that distribution, I simply, what do? I guess all I did here was I just used the associative property and I multiplied A inverse by A, so I eliminated these two because they become 1, right? But I left these two even though they become 1 also. And what I'm going to now do is I'm going to take the A inverse, this little mess right here is supposed to be A inverse, right? I take the two A inverses and I undistribute it to here. And then I recognize that this is the geometric product of x with A. This is the metric contraction of x with A. So the geometric product minus the metric contraction is, in fact, the wedge product. So that is very simply reduced. So this whole term reduces to the wedge product of x with A multiplied by A inverse on the right, and voila, that is your perpendicular vector. So this thing needs to be a vector. So this is a bivector, this is a vector, right? And whenever you see these A inverses, you shouldn't be bugged. Sometimes they write it like this, which I always found a little annoying. I don't like that form, but because dividing by a vector is kind of weird. But yeah, once you realize dividing by a vector is just multiplying by an inverse vector, that weirdness goes away pretty quick. But just understanding that A inverse is A over, in the case here, magnitude of A, or actually you know what, I'm going to just start writing this as A over A squared, right? Because if you're in the 3D geometric algebra, A squared will always be positive anyway, and if you're in 4D, it could be negative, and that would matter. So anyway, the point is, you know that this is a number in the denominator, so you know that this is a vector in the numerator, so you know this is a vector here, right? And when you look at this, you say, well, immediately you know it has no trivector. It's a product of a bivector with a vector, so the result has to be a trivector and a regular vector, a grade 1 object and a grade 3 object. But the grade 3 object is 0 because this A here is actually co-aligned with that A there. So this A is linearly dependent on that A, so you know the trivector goes away, and all that you're left with is the vector. And we know how to do that vector calculation. It's going to be A dot AX minus X dot AA, right? Is what it's going to be. That is, it's going to be this thing right here, right? That's what this is, because that's sort of a memorized, it's a memorized property that I've got carried around in my head. So that's a way we calculate the rejection. The rejection is this bivector. The rejection of x on A is the bivector of x with A times A inverse, right? So we have those two formulas in our hip pocket. And now we are going to understand the reflection. Now, to make sense of this, by going through the literature, there's actually a couple different ways they think of it. The first way is taking a vector x and reflecting it through A, which is actually taking the reflection of the vector x, and you take vector A, and you're going to actually push x across A, which basically means you're taking the perpendicular component of x, right, x perpendicular, and you're actually taking its negative, and you end up with a new vector on the other side of A, reflected through A. And this is actually done when people are working a lot with two-dimensional geometric algebra. But that is really not the good way, I think, overall to think about it. Instead, we want to flip this parallel part. So we're not really reflecting through A, we're kind of reflecting over and around A. And the right way to think of it is about you're reflecting through a plane. Like a plane is more like a mirror anyway, right? So you're reflecting through a plane that is perpendicular to the vector A. And when you think of it that way, then of course you're going to take the part that's parallel to A and change its sign, and of course the perpendicular part won't change sign at all. And turns out to be the correct way of looking at things. We're always reflecting through planes, but we're identifying the planes through their normal vectors. Now, you might immediately say, well, you've already mentioned a few times that in higher dimensional spaces, a plane does not have a single unique normal vector. There are many normal vectors. For example, if this was the E1, 2 plane, right? If that was the plane defined by E1 wedge E2, well, E3 is normal to that, E4 is normal to that, E5 is normal to that, all the way to the En, where n is the dimensionality of your geometric algebra. Every one of these vectors is normal to that plane E1, 2. So this clearly doesn't work. But geometric algebra saves its own day by saying, well, no, we're just doing this because this is three-dimensional, so this line, which is actually a plane coming out of the whiteboard, you've got to think of that as a hyperplane. And it is the hyperplane normal to A. And in any d-dimensional space, a hyperplane has d minus 1 dimensions. And every hyperplane of d minus 1 dimensions does, in fact, have a unique normal, or an identifiable single normal vector. So what we're actually doing is we're reflecting x through or across a hyperplane in higher dimensions. And this is done using this very simple prescription, right? When you reflect it through this hyperplane, you still get a vector, but it's a little bit hard to picture this hyperplane. But it works fine in 3 dimensions for us to use 3 dimensions to understand it, and that's what we're going to do. So we can just sort of work through the math of how to do this reflection. The reflection is obviously the perpendicular part of x. So x reflected in this hyperplane. So this r represents the reflection through this hyperplane as identified by the vector A. So you could, in fact, write, this is RA. So the A actually identifies, I'll put a hat there to show it's a unit vector. That little A hat is telling me what the unit vector of the hyperplane is, which in turn identifies the hyperplane, and R tells me I'm reflecting the vector X in that hyperplane. And obviously, throughout this, I'm not putting little arrows on X. Sometimes I do, sometimes I don't. It depends. We're only dealing with vectors here, so it's kind of silly to do it all the time. All right, so how do we do this? Well, the perpendicular part of x stays the same, but we change the sign of the parallel part. So we're trying to calculate this. That's the definition of XR. Well, a pretty typical trick in geometric algebra is to multiply by the geometric product of a vector with its own inverse, because this always equals 1, right? So we're not really doing anything new there. So I just distribute, because everything is linear, I just distribute it right through to get this expression here. And now what I'm going to do is I'm going to commute the perpendicular part of x with A. Now, A is, by definition, this perpendicularity is with A. So x perpendicular is by its very definition perpendicular to A. So these two commute just fine. So this just straight up commutes. And this a perpendicular is, wait, what did I just say? This is the perpendicular part anti-commutes with A. It anti-commutes with A, right? So yeah, perpendicular vectors, just like unit vectors, we do this all the time. E1, E2 equals minus E2, E1. Well, A and X are perpendicular to each other, just like these unit vectors, so they anti-commute. So when I reverse their order, like I do here, I pick up this minus sign. On the other hand, this part that's parallel to A, well, if A and A are parallel, you know that it's bivector, the geometric product of A and X parallel, the bivector part is 0, so all that's left is the scalar part. So this thing commutes just fine. And that's where you pick up, we commute these two to get these two here, right? We take these two and commute right here. So now we've got these two minus signs here, and those two minus signs we just pull out in front to get this big minus sign right here, and then X perpendicular and X parallel get summed together, and we pull the two A's on the left out to the left, and we pull the A inverses on the left to the left, and we pull the A's to the right. This guy becomes X, then you get A and minus A inverse, and this is the formula for that equals the reflection. So this beautiful formula is a pretty simple formula for reflecting X in the hyperplane that is orthogonal to the vector A, orthogonal to the vector A. So now that we've defined or we've learned how to calculate the reflection through a hyperplane, as we've just described by this formula, the next question is, well, what about two hyperplanes? Well, you just repeat the process, right? The reflection R is through the hyperplane orthogonal to the vector A, and S is the hyperplane orthogonal to the vector B. Well, here's X. This is X reflected through a hyperplane orthogonal to the vector A, and then by multiplying by B and minus B inverse, that's taking the result of this and reflecting it again. So this is a composition of functions, really, is what this is. And you take the two minus signs out, and they clear, and you're left with B inverse A inverse X AB. And this is the reflection through two hyperplanes. Now, the thing that's important to appreciate here, which is the obscure but interesting and ultra super important fact, is that let's look at this diagram here and see what this next super important fact is. If A is given by this vector right here, right? This is the vector A, and then this is the vector B. So what we're going to do is we're going to take a vector X, it's this blue vector, and we are going to reflect X first through the hyperplane orthogonal to A, which is, here's the hyperplane orthogonal to A, and then through the hyperplane orthogonal to B, which is this line here. So that first reflection takes X, and remember, we're sort of switching the, we're taking the parallel component of X and changing its sign, so X moves from there to here, right? So this is XR. So this is XR. So that's the first reflection. And then the second reflection is through this plane B, right? And so this ultimately here is SR, right? R first, S second. That's what I mean by XSR. And I guess my vector needs a little point on it, like that. So, but what's important to understand about this geometric construction is that the ultimate angle of this whole process, that means the angle that X is rotated by these two reflections, is twice the angle between alpha and beta, which means that if I want to control the amount of rotation of the angle x, I just pick an alpha and beta that have half the angle that I want to rotate. If I want to rotate by pi, I pick theta to be pi over 2. If I want to multiply it by pi over 4, I take theta to be pi over 8, right? But this is a little obscure geometric fact that reflecting between two planes, normal to two vectors, is equivalent to a rotation of the same vector by twice the angle between these two planes, or between these two normals. And that little obscure fact, although it's, relatively well known, I'm sure, for centuries, never was that important, and I certainly have never thought about it until geometric algebra kind of forced me to. But now it's telling me that if I want to rotate a vector x through an angle of 2 theta, I need to just execute a reflection that through two planes that and I can pick A and B to be any two vectors with an angle theta between them, and execute these rotations or these reflections that I just did, right? This reflection right here, right? This is the reflection. I just pick any A and B that has the right angle, and this reflection, this double reflection, I guess, will be a rotation of x. And so taking that to heart, I'm going to call the bivector of any two vectors, I'm going to call it a rotor if A and B are unit vectors, right? Because the length of A and B really doesn't matter. Because actually, if you execute this product, right, you'll notice that the length cancels out. Because on this side here, you have a b squared and an a squared in the denominator. Say A and B were not unit vectors. These inverses would be BA with two squares in the denominator like that. Turns out that when you chug through all this, those the lengths of A and B turn out not to matter, right? Because this is a reflection, right? This is a reflection, so why should it matter? So going forward, let's just assume A and B are unit vectors, and then we're going to say you take two unit vectors, you form their bivector, or you form their geometric product, and we're going to call that a rotor or a spinner, right? And so now we have an object that we're actually sort of treating in a way as an operator, right? We're basically saying if I want to rotate an object by theta degrees, right? I have a theta degree rotation, and that object is x. That is an operation, right? So R is an operator acting on x. Well, the method of that operation is I create an appropriate rotor and multiply x, geometric multiply x on the right by the rotor and on the left by the inverse of the rotor. And that would be the effect of operating on x by an operator that rotates x theta degrees. So this is sort of the operator form, and this is the geometric algebra implementation form. But what's really important is that this works for any dimension, right? Any dimension, all I have to do is find two vectors in that dimensional space that have the right angle between them, and I can create a rotor. Now, I don't know if absolutely 100% rotors are always defined with unit vectors. The paper I'm reading, or the various papers I read, clearly there's no reason not to use unit vectors here, so why wouldn't you? Anyway, they do make it a lot simpler because they want your rotors to be written in this form, right? A nice, clean cosine plus sine, and that would only happen if A and B were unit vectors, right? So we take our rotor, we break it up in, it's a geometric product of two vectors, so we know it has this classic form of the grade 0 part and the grade 2 part, right? The grade 0 part for two unit vectors is going to be the cosine of the angle between them, because the two magnitudes are 1, and the grade 2 part, well, that's the area of a parallelogram covered by the vectors A and B, right? Bounded by the vectors A and B. Well, that area is the magnitude of A times the magnitude of AB times the sine of the angle between them, but magnitudes of A and B are 1 because we're dealing with unit vectors now. So you just have this sine factor, And then I is any bivector that is made of orthogonal components that defines the same plane as A and B. And we know that we can do that because we did that in a previous lesson. So that guy we might call W hat V hat, where W hat dot V hat equals 0. And I would equal W hat wedge V hat, right? Wedge V hat, like this, which equals W hat V hat, right? That's the geometric product equals just the wedge product because we've set up W and V, so their dot product is 0. So once I have this structure, and I know that I squared equals -1, because that's always the case, right? Because W hat V hat, W hat V hat, since W and V were designed to be orthogonal, right? I end up with W hat V hat V hat W hat. That's one switch, so I get a minus sign. That's V squared, so that's a number. So that leaves behind W squared, which is another number. They're unit vectors, right? So that number is 1, that number is 1. So this whole thing equals -1. Oops. Equals -1, like that. So with that, once I know that this bivector I squares to -1, then kaboom, this immediately can be written in this Euler form. And that's a vector, and this part here is a vector because I squared is -1, right? So you have beta squared x. So that becomes a vector, and you end up with alpha squared plus beta squared x. So that's actually the original vector, interestingly. And because alpha squared and beta squared, that's cosine squared plus sine squared, so that's 1. So that's the original vector. And now, if you look at this part, all we want to do right now is just show that it's a vector. Well, this piece here, this is a vector times a bivector. So normally a vector times a bivector is a vector times a bivector is going to have a vector part and a trivector part. Well, the vector part we don't care about because the vector part is what we're trying to show. We're trying to show that it has a vector part. But we do need to show that the trivector part goes away. And that brings up a bit of a subtlety which I did not point out earlier, so I'm going to have to go back and point it out now. When I drew this picture, the part that you may have missed is that x, of course you missed it because it's literally drawn this way, right? X is in the plane of A and B already, right? So it just shifts over in this plane. But it doesn't have to be that way. X does not have to be in the plane of A and B, and it'll still rotate, right? What'll end up happening, and I'll show you why in a moment, is that this becomes X parallel. But now, and this is why when you read a lot of different books and they take different approaches, you have to be very careful. That parallel means the part of X that's in the plane of A and B, right? It's not parallel to A, it's not this piece. It's not parallel to B, it's not that piece, right? It's actually the part of X that lies in the plane of A and B, and that's what moves. And the part that's perpendicular, right, the part that lives here and comes, I guess, out of the board, right, that would be X perpendicular, right? So you got to sort of imagine something standing right here, coming right out of the whiteboard. That's the perpendicular part. That part doesn't change at all. That part is absolutely fixed. So this was one of the reasons we did some of the work in our last lesson. So let me show you how this works. We imagine this situation where X is out of the plane of W and V, where W and V now, that's what I is, right? I equals W hat V hat, right? It's that geometric product. And so X has two pieces, right? X has a component that is in the plane, right? I'll make it a dotted line. And that we'll call X parallel, right? So this is X parallel. Then it has this part that's out of the plane, right? Let's see, let me shorten X parallel a little bit. So this picture looks a little better. and this part that's out of the planes like that, and that's x perpendicular, right? So now our claim is that the rotated form of x, so x rotated, equals the rotor inverse acting on x followed by the rotor. Well, now I break x down. I'm going to make a whole bunch of substitutions. Let's go to black here. This will be E. Well, actually, I've done it over here. I forgot. So this is the process. Now, x, so the rotors can be replaced by these two expressions where phi is the angle of rotation we want to derive on x, and I is the bivector of the plane that we're going to do this rotation in, or it's actually the plane of the two, the plane defined by the two normal vectors, right? Which is where the rotation is happening, right? The reflections are happening in these perpendicular planes. Let me show you that. Remember, these perpendicular planes, that's where reflections are happening. So there's no rotations going on in these planes. The rotation of this piece is purely in the plane given by, defined by A and B. And so that plane we're calling defined by I. So we've got our i's, we create our two r's with these exponentials, and then I break x into the parallel part, and the perpendicular part, where now parallel means in the plane of I, and perpendicular means not in the plane of I, out of the plane of I. So everything being linear, I'm just going to bring everything together, just like this, right? I'm just simply distributing through with e to the minus phi over 2 and e to the plus phi over 2. So I end up with these two expressions. But you'll remember in the last lesson, we studied the commutation of these two ideas, of these two things, right? We studied how a vector that's perpendicular to I will commute with an exponential, and a vector that's parallel to I, which will commute with an exponential. And what we learned is if you're perpendicular to the bivector that's in this argument of the exponential, if the vector is perpendicular to it, this geometric product here, because remember, this is a geometric product of two vectors. So this is a bivector plus a scalar, right? That's what this is. But if it's perpendicular to this plane, it's going to just straight up commute. This is going to straight up commute. So this expression here is going to be e to the minus phi over 2i times e to the phi over 2i x perp, right? And these two are just going to add up to 0. So you're going to end up with e to 0, which is just x perp. So this entire side over here is going to just cancel. This is all going to cancel to 1. But more importantly, the other one, we know that if you're parallel to the plane defined by this bivector I, this commutation product produces a, I don't want to say it anti-commutes because it's not a minus sign here, but it makes the exponent anti-commute because we proved that the last lesson. We proved that if you're in the plane of this bivector, you can pseudo-anti-commute with the exponential, but the minus sign appears in the exponential, which this isn't a surprise because this is just a Taylor series where, it's a sum of things, so you're just anti-commuting with each piece. So this appears linearly in each piece at some point, so that's not a big surprise. But these exponents now add up to phi, right? So this guy here is going to be plus e to the minus phi I x parallel, which is also, we can play the same game, x parallel e to the phi I, like that, right? So we can do it either way, left or right. If it's on the left, you got a minus sign. If it's on the right, you get a plus sign. But the rotation is always this number of degrees in the sense of I, right? So if in our case here, if I is WV, the rotation will be in that, the positive rotation will be from W towards V. That would be the positive rotational sense. So the answer is it's equal to x perpendicular, which doesn't change because that's 1, plus x parallel e to the phi I. Right? And so now if we had started this whole analysis in 2 dimensions, we would have learned that a rotation of any vector in the 2-dimensional plane would immediately rotate in this fashion, right? We could study this from the beginning. And then we have to say, yeah, that's good, but the plane is too simple. In 3 dimensions, you really have to go to this expression to rotate a vector. Because remember, every vector in 2 dimensions, in 2-dimensional geometric algebra, every vector is parallel, right? Every vector is in the plane of I. There's only one I, because there's only one plane, right? So that's why 2 dimensions, I think, is a little too simple, because you end up basically proving that this is how rotations are done. Rotations are just done R times the rotor, right? There's no need to do R inverse in 2 dimensions because in 2 dimensions, every vector commutes with R. So if I wrote R inverse like this, I would just immediately, well, I'm sorry, and not every vector commutes with R. Every vector commutes in this sense, right? So, you would have e to the minus phi over 2 I, and then you would immediately, in every case, just turn it into e to the minus phi over 2 I x, because every x is parallel. There is no such thing as x perp in 2 dimensions. So 2 dimensions is too simple for this analysis, in my opinion. So that's my little contribution, is to just skip 2 dimensions and go right to 3. But in the end, you do find that the parallel part just rotates very nice and simply, but the perpendicular part remains the same. So what's basically kind of going on is ultimately this piece here, right, rotates to twice of angle theta, so it rotates to there, and then, which means, and this piece here stays the same, so the whole thing just sort of moves like that, where this is now the new x parallel is this part. So that's kind of cool. There's a lot of different pictures you can see online or in papers about describing this, but basically that is the story. The story of these rotations is that you're taking the parallel part, the part that's in the plane of the pseudovector, that's defined by the 2 vectors that we're using to define the plane of rotation. And now we actually do talk about a plane of rotation, right, being these defined by these 2 vectors that are actually the normal vectors associated with the hyperplanes of reflection, right? So that kind of seems complicated, but it's just a way of getting us there, right? It's a way of getting us there. We define these 2 vectors because we're going to talk about 2 reflections, and that gives us this notion of phi and 2 phi, right? Which I didn't prove, by the way. I didn't show that a reflection from of a vector through this the plane normal to A and the plane normal to B will actually be 2 phi, but it is. And that's really, really remarkable. Okay, so so I guess that brings us back to this, right? I needed to show that this was a vector, so I needed to show that the trivectors went away. And so we showed that, okay, this vector here, x, times this bivector, well, the perpendicular part we know will just straight up, well, I guess we actually have to work it out, right? We have to say, all right, I is actually W hat wedge V hat, right? So now we have, okay, so this part, this perpendicular part with W wedge V, well, it's x perpendicular wedge W wedge V. We know that that's the inflation part. We already know that this product's contraction part will be 0 because x perpendicular is perpendicular to W, perpendicular to V, so all of the dot products involved in that geometric product will go to 0. So this guy, well, if I flip x once, I pick up a minus sign, and then I flip it over here, that minus sign goes away, so I get this. So x perp I equals ix. So if I flip the perpendicular, so the perpendicular parts end up canceling, right? Because you don't lose this minus sign. So what about the parallel parts? Well, if I change this perpendicular to parallel, right? Well, the definition of parallel is that it's in the plane of W and Z. So that part goes to 0 right away, right? So the only part of this x parallel geometric product with W wedge V is the contraction part. So all of this is 0. And well, what is the contraction part of x perpendicular times geometric product W wedge V? What's the contraction part of that? Well, it's x parallel dot W hat V hat minus x parallel dot V hat W hat. Well, that's a vector minus a vector, so that's a vector. So this whole thing ends up being a vector. So you have a vector, this whole thing here we call the vector V, so you end up with a vector W. So that's just to show, all that's to show that a rotor times an arbitrary vector is a rotor. And we took a little bit of a divergence, a digression in the middle of that to show this really important fact that this rotor applies to any vector, right? That some of which is in the plane of I and some of which is not. Now just be careful. Sometimes we've written a perp to mean in the plane of I, and a parallel to mean in the plane of I, right? And a perpendicular we meant to mean out of the plane of I. But then earlier, when we talk about reflections, we're talking about the projection of x on a vector A as a parallel, and the projection of the rejection of x on a vector A as a perp. So those are two different parallel and perpendiculars, right? This would be x perp. So again, it's all notation and it's all contextual. And so then there's one last thing about rotors I want to talk about in this lesson. And this to me is really, really almost a big selling point for geometric algebra. And that is, say I took the geometric product of a whole bunch of vectors, A, B, C, and D, right? Now every blade, right, every, say, K blade is basically a sum of objects that look like this, right? It's the sum of a bunch of geometric products of orthogonal unit vectors. The way we've been doing it is, AK is going to be some number A, say 1, 2, 3, E1, E2, E3, or E1, 2, 3, depending on how we're writing it at the time. I noticed, by the way, Mathematica tends to do this. There's a Mathematica package that I'll try to show off in a lesson or two. That's really fun. And I kind of wished it would do this, but it actually uses this notation. But the point is that any K-blade can be written as the sum of terms of these geometric product of orthogonal vectors. And any multivector A can be written as the sum of K-blades, right? From K equals 0 to n in your n-dimensional space. So imagine taking just an arbitrary blade, which is sort of represented by this geometric product, and sticking it between two rotors. Well, that would, if this was just a vector, we know that that would rotate the vector by an amount given by the definition of our r, which is e to the I phi over 2. It would rotate it by an angle of phi in the plane defined by whatever pseudovector we throw up there in our definition of r. So perhaps I should be a little more specific now, because we're talking about an arbitrary space, an arbitrary rotation. So I should probably go omega v, where we assume omega and v are orthogonal unit vectors, phi over 2. That way you kind of look at this and you don't forget that that is the pseudovector. This guy here is a pseudovector in a plane of a certain plane sitting out there in n-dimensional space, right? Any dimensionality. So once I've chosen this and I've got r, and r inverse, of course, is totally trivial. You just throw a minus sign on it, right? But look what I can do. I can stick r inverse everywhere in these blades, right? Because r inverse is just 1. So this is exactly the same thing as this. But then I just regroup like this, right? I just regroup like that, and all of a sudden I have the rotated r, the rotated b, the rotated c, and the rotated d multiplied together. So if I want the rotated version of any blade, right, and by linearity, any multivector, all I have to do is multiply by r inverse on the back and r inverse on the front, and I suddenly get the whole thing rotated. So it doesn't matter what multivector you throw in between r inverse and r. So everything I proved up here for a vector is true actually for any multivector in the space. You can rotate anything in the vector space. You can multiply a bivector, a trivector, a pseudoscalar. You can multiply a 10-dimensional thingy, whatever, just by making one pre and post multiplication in geometric algebra. And that is a big selling point, because if you're doing this in normal vector analysis, for every dimensionality of thing, for every strange thing you threw in here, you'd have to come up with a new representation for how that thing rotates. And that's not true in geometric algebra. In geometric algebra, it's very clean. All you have to do is take this rotor and execute this multiplication. So anyway, I'm going to stop there, and we will pick up this subject again. I'm not sure what the next topic will be in our next lesson. So I'll see you next time.